I'm going to talk about this application. Talk will have three parts. I'll tell you about the problem. I'll tell you about the solution described in the BSSA paper, the net visa system, and then I'll describe some current work on a more complicated and difficult and potentially better approach. Okay, so the Test Ban Treaty is about banning nuclear explosions on the Earth. And just to give you a little historical background, there have been 2,054 of those. Two of them in Japan killed about 200,000 people. Another 100,000 people have died as a result of tests and nuclear fallout from those tests. So here's a little picture of a test. This is a crater in Nevada. So this test excavated 12 million tons of earth. And just to give you a sense of scale, this is 1/500th the size of the largest ever nuclear test, which was carried out in Siberia. So for a long time, people have been trying to stop testing. Back in 1958, President Eisenhower wrote to Khrushchev, who was leader of the Soviet Union, saying that we need to stop testing because testing is creating international tension. It's facilitating an arms race that may destroy the human race. And he said that failure to achieve a ban would be essentially the biggest failure of any American administration in history. So finally, almost 40 years later, the treaty was opened for signature in 1996 under the auspices of the UN, and almost all nations have signed the treaty. And it's a very strong treaty. What it says is if there's evidence of violation, that an international force can occupy 1,000 square kilometers of your territory to search for proof of violation, and then there are various consequences for that. Unfortunately, the US Senate rejected the treaty, and so the treaty is not currently in force, and they claim that it was too hard to monitor. So what does that mean? Well, there is a monitoring system. It's called the International Monitoring System. It has currently 278 stations around the world. Most of them are seismic stations, and those are the ones that are providing the real data. A lot of the other ones are radionuclide stations, which detect the after effects of an explosion and try to trace it back. That's the sort of smoking gun sensors. So a seismic station produces this kind of thing. You've probably seen these. This is an earthquake happening, a 6.5 earthquake happening near Japan. It's being measured 9,700 kilometers away. So these stations are very, very sensitive. They can measure ground motion of 1 nanometer, and they can measure children jumping in the playground several miles away. You can see the morning exercises of Japanese school children in these seismographic records. Okay, so this is a very big earthquake, obviously. A nuclear test might be, if it's well decoupled, might be as small as that little tiny blip. So, so we're trying to find these things, these needles in a haystack. And what you have to do to build a seismic monitoring system is every day the system has to produce a bulletin which lists every single seismic event that has occurred, along with its time, its location, depth, and magnitude. And the UN doesn't actually say, oh, and this is a nuclear test. They just say, well, there was a seismic event of a certain magnitude, very close to the surface in an area where there's never previously been any natural seismic activity in North Korea or whatever, and you make the choice. Okay, so you might think, well, how hard can it be to detect nuclear explosions? I mean, enormous great things. Turns out to be very difficult. The Earth is still a large place, and the Comprehensive Test Ban Treaty Organization has spent more than a decade and well over $1 billion developing this monitoring system, of which about $100 million goes into the monitoring algorithms. And still, their automated system has a recall of only 69%. So 31% of events in the magnitude range of interest go undetected. And so what they do is they have a full-time team of human analysts who basically correct all the errors that the automated system makes and find all the events that it missed. And even so, there are studies showing that that combined machine and human system is still unreliable below a 1 kiloton magnitude, which so there are ways of decoupling a test so that its apparent magnitude is much less than the true yield of the explosion. So that's a serious problem. So why is it hard? Right? Why is it that you can't detect a nuclear explosion? One of the reasons is that the Earth is a not only large but very noisy place. So there are about 10,000 detections in this network of stations every day, where detection is simply a signal that's large enough to be potentially interesting. And 90% of those are false detections. They don't actually correspond to any large seismic event. They typically correspond to very small seismic events occurring very close to the station. So ice cracking, so lots of stations in the Arctic and Antarctica subject to ice cracking, large waves hitting the shore, all kinds of things like this. Also, the signals are very, very complicated. So a single seismic event can generate over 100 different wave types, where a wave type is characterized by its physical propagation mechanism, which can be parallel waves or shear waves like this, and various other kinds, surface waves, body waves, and also the path they take through the Earth. They can go around the crust, they can go through the middle, some of them go through the core, some of them go around the core and come back out the other side. So there's more than 100 different types of waves, and they have very different velocities and paths. And some of those paths take them many hours to get from the event to the detector. And so when you've got many events occurring around the world and their signals take many, many hours to reach the stations, the resulting sequence of detections can be completely mixed up. So it's like having 1,000 conversations that are all scrambled and then all played simultaneously through your ears. So it's a difficult problem. And the approach that's traditionally taken is the same as in almost all scientific data analysis. It's a bottom-up pipeline. Okay, so you start with the data, you pre-process it, you pre-process it some more, you pre-process some more, and then you output the results. Okay, so what we typically do, what the UN does, is take the waveform signals and then find, through a method called station processing, these detections, which are basically peaks in the signal compared to the surrounding signal levels. And then those are grouped together using what's called the global associator algorithm, or GA, to form events. So the approach we took was what you might expect. If you're a Bayesian, you say, well, let's build a model. Let's put in everything we know about this problem into a probabilistic model. That's a generative form. So it says, if an event takes place, what do we expect to see in the recorded detections? And then we do inference in the other direction using Bayes' rule. So it's this very traditional approach. The model itself is quite complicated because the world is complicated, and also we don't know what events occur. So there's number uncertainty or existence uncertainty about the events and the detections. A more sophisticated approach would be to try to model the raw data itself. So not have this pre-processing step that does some kind of thresholding, but actually model the detailed raw signal data itself. So I'll talk about that approach later. Okay, so let's start with this detection-based Bayesian monitoring approach. In order to explain the model, I have to teach you some seismology. It's a very, very easy field, at least in part one. So you have some stations, and an event occurs, and then a wave is propagated from the event and reaches the station. And if you're lucky, that station records a blip, or maybe more than one blip. It also records some other blips. So the red blips that came from the red event, and then there are black blips that maybe were background noise. Meanwhile, a blue event takes place, and signal goes out from there, gets to the station. So that station records a blip. And notice now that we've got a blue blip occurring before the red blip, even though the blue event occurred after the red event. So that's this reversal in time ordering as a result of spatial dispersal. Okay, so at the end, you've got a sequence of blips at every station. And notice the blips are no longer colored, right? That's unfortunate. It would be nice if they were, but they aren't. They're just blips. And so you've got this complicated combinatorial association problem of figuring out which blips belong together that came from the same event. Once you solve that, if you knew the answer to that question, then it's just a question of triangulation, except that these things don't move in straight lines, and it's not exactly triangulation, but basically that's what's going on. Okay. All right, so we wrote a blog model. So blog is a language for writing complicated models. It's like many other models, many other modeling languages, except that it does allow us to talk about objects that we're not sure exist. And in this case, we can talk about events and detections without knowing whether or not there are any events or detections. So the model describes the occurrence or potential occurrence of events, how frequent they are likely to be, where they're likely to occur, their magnitude, the probability that an event produces a detection at a given station, what that detection will look like, when it's going to arrive, the time, how big it will be, the amplitude, and the direction that it would come from, given where it took place. We talk about the measurement uncertainty because there's lots and lots of error in the measurement process itself. And then there's also these noise processes that produce detections without there being really significant seismic events. So the advantages of doing this model-based Bayesian approach, one is that you can put in a lot of prior knowledge. So geophysicists know lots and lots about the world, so we don't have to do model-free, data-driven stuff. We can put in lots of physics. We can also use a lot of historical data to quantify these models. And as a result, we get good behavior from the system, and we have happy geophysicists. And that's what really matters if you want to get something adopted. The geophysicists are not just happy because it works well. In fact, if it worked well and was a black box, they would reject it completely. So they're happy because they get to put in their prior knowledge, and they understand what our system is doing because we can point to the prior knowledge. And if something isn't working, we can say, well, do you think that this independence assumption is correct? Or do you think that that model needs to be nonlinear instead of linear? And then we can have a discussion about physics. So let's go through the model step by step. This is, I'm not going to go in detail, but this is the blog model that I wrote when I first understood the problem. And I'll just show you little bits and pieces of it. The first piece I've highlighted in blue is the part that talks about the entities that may or may not exist. So the number of seismic events is Poisson, proportional to the length of the time interval that we're looking at. And then the number of detections that occur, there are two kinds of detections. There are detections that just occur at a station, and they don't have a source. So these are the noise events, and there's some background rate for those. And then there are detections that occur as a result of an event. So they have an event that caused them. They have a phase, which is the type of the wave that's arriving, shear wave, parallel wave, and so on. And that will depend on some detection probability model that talks about amplitude and distance and background noise and so on. Okay, so the locations of events are described by a mixture model. There are two components to this mixture. There is a spatial prior for natural seismicity, and then there's a prior for shall we say, man-made seismicity. The man-made seismicity model has to be uniform because the treaty does not allow us to have any bias whatsoever about where events might occur. So to learn the spatial part of that prior, we can look at historical events, and we can do a cross-validated kernel density estimate, and we get a prior that looks like this. And one surprising thing about this, if you live in California, you think you're an earthquake country. You are not. Pretty much 90% of all the stuff happens over in Indonesia in the bottom right section. Okay, detection probability model is a logistic regression model, and it has shrinkage, so it's actually shared across all the stations, because some stations don't have enough data, so they get to share data from other stations, whereas stations that have lots of data get to learn their own detection probability model. And here we show the results from that logistic regression model at Alice Springs. So a p-phase wave has a high probability of being detected. The x-axis here is the distance from the event to the station, and the S phase has a very small probability of being detected. Another important part of the model is the onset time. So when do we expect the signal to arrive at the station? And this depends on the distance between the event and the station. And the physicists already have a complicated model, the geo-travel time function, which is a deterministic function that assumes a radially symmetric density model of the Earth. And from that model, you can calculate travel times. But it's not exactly correct. So we have to put in a residual correction, which is parabolic in our model, and turns out to have a Laplace, or approximately a Laplace distribution, which was a surprise to the geophysicists. They had been assuming normal errors in all of their work going back to 1910. But this is still a pretty good model. So you can see the errors are around 2 seconds for a transit time of 15 minutes. So it's a pretty accurate model nonetheless. The direction model, the azimuth, which is the direction the wave arrives from, again has a Laplacian error along with a uniform component, because sometimes the direction calculation is done by a kind of beamforming, and sometimes the beamforming fails as a result of aliasing, and you get essentially a random direction as a result of that. Finally, the observed phase, so the type of the wave that's arriving, there are 14 wave types that are recognized by the UN software. Almost all the time, the software says that it's a P wave, even when it isn't. And unfortunately, their existing classifier does worse than choosing the most common answer. And it is, in fact, a neural net, I'm told. So this is one of the things that took a while to get through when discussing these things with the geophysicists. They tend to not distinguish between the phase that their system reports and the true phase in their software. And so once the system has reported that this is let's say a PN, then it stays as a PN. And it's very important to get across to the geophysicist that the system can classify something as a PN initially, but that's just a guess, and there's a true phase that we don't know, and the system has to be able to infer that as part of its model. Okay. So to do inference, it's not terribly valuable to go through this in great detail. It's, as you can imagine, it does split merge, birth, death kinds of processes to search through the combinatorial space of associations and figure out how many events there are. It took us a while to get this to run fast, about 3 months of work from when we first built the model. But now it runs faster than real time, even when we have a very large event like the Sumatra or the Tohoku earthquakes, which generate as much as 50 times more detections than usual. We can handle that in real time by running in parallel on about 100 nodes. Now, for the client, for the geophysicists, it was a bit of a shock that the algorithm is not very interesting, because they're used to thinking, okay, there's geophysics over here and there's algorithm over there, right? And there isn't really any communication between geophysics and algorithm. You try to fiddle with your algorithm to make it work better, and that's what you do with software, and it has nothing to do with geophysics. But what we're trying to tell them here is, no, the algorithm is fixed. It just does Bayesian inference or map computation. So ignore the algorithm. Forget about the algorithm. Just make the geophysics better. So if you want to get better results, all you have to do is tell us more about the physics of the problem, and we can put it into the model, and then we get the right answer. So that was a big change in their mindset. Okay, so does it work? Yes. We've done the usual training and testing. This is some data from a 12-week train test, but we've also done 3 years of training and 1 year of testing and so on. And we're comparing against the human expert output from all the expert seismic analysts. And this is the error rate for the UN system. That's the fraction of events that are missed. And this is the error rate for our system. So it's about a 2.5 reduction in missed events compared to their system. So we were fairly happy with that. I realize this is not as significant as a 1% improvement in Netflix recommendation quality, but there it is. Okay, so we also looked at some other cases where we actually have better access to ground truth from very, very dense regional networks. So the UN system is a global network, which is quite sparse, but if you go to Japan, they have tens of thousands of seismic detectors, and they can detect everything. So you can treat those as a better form of ground truth than the human experts, the LEB, the Late Event Bulletin, as it's called. And there we find that actually our system was improving over the human expert output. So we had, in some cases, 100% more correct detections in a given region than the human experts, even though we're using exactly the same detector network. And then lastly, here's some results in North Korea. So this is from the 2013 test. On the top left, you see the UN's final consensus location for the nuclear explosion that took place. And then the blue square is our consensus location. And then the black cross down towards the lower right is the place where the tunnel entrance was spotted in satellite photographs. And so I think we have a better location than the UN does on that. Okay. So politics as usual, we can't get our system actually deployed until all the member states agree to deploy it. So we're waiting for that vote. Okay. So very briefly, I'll talk about the SIG-VISA approach, which is this method of generative model going all the way down to the raw signal, which is much more complicated. I apologize for, okay, there we go. Sorry about that. All right. Yeah, okay. So in the SIG-VISA model, we have to produce something that actually says not only when is a blip going to arrive and how big is the blip going to be, but what exactly is it going to look like. So we have to explain the entire waveform sequence, including all the noise and everything else. So there's a notion in geophysics of a template model. So we expect that the general shape of an arrival will be a sharp onset followed by some exponential decay. And then there's a wiggle model. So the wiggle model says that this nice smooth exponential decay is actually going to be changed, and it'll look like some very complicated wiggly thing. And then there's all the background noise, which is signal arriving at the station that's not from this seismic event, but it's just background noise, which we use an autoregressive model for that. And those three things, so we multiply the template by the modulation wiggle, we add the background noise, and that is our prediction for what the observed signal actually looks like. So this turns out to be working fairly well, and we've shown already that we can find the evidence of signal arriving even when the existing detectors have failed to detect anything at all. So here's a detector in New Caledonia that did actually record something from the North Korean test in 2009, but it wasn't detected by the UN system at all. But we can show that with a template fit, we can actually recover some signal and get actually more information about the location of the event from this. We can also do things that the existing system can't, like deal with superposition of signals. So when you have lots of events occurring and the signal traces can be many hundreds of seconds, then there's actually lots of superposition going on. And when you have a signal model, as opposed to a blip model, you can actually handle that perfectly naturally. So one question is, if you're doing some kind of split merge birth-death process, you have to have a way of actually birthing these templates. And previously, the blip detector is what's birthing the template, right? It says, you know, there's a blip, so I'm going to assume that an event signal was arriving here. So if you don't want to use a threshold detector, then what can you use as a way of proposing these new template arrivals? And the answer is to actually just do a birth proposal that's proportional to, in this case, the square of the unexplained signal. Okay, so you just look around in the signal and find, you know, are there places where there's a lot of signal and we don't have a template already explaining that? And then you birth, the probability of birthing is proportional to the square of that error. So just to show you a little movie, right, so here's some signal, and we birth a new template right there, and then we move it gradually, and we birth another one, and we move them together so they jointly explain this piece of signal very well. Okay, so just to show you that this actually works, here's a little movie for the 2009 North Korean test. So we're starting out with a small number of template arrivals that are not fitting the data very well. And we've got an initial location estimate which is way off up here in the corner, so several hundred kilometers away from the true event. And as we run the MCMC process, you see that very quickly it converges to the right location and the templates move themselves to fit the data very nicely. Okay, so a couple of minutes on wiggles. So far I've just showed you what happens with templates plus the noise model. But the wiggles themselves turned out to be very interesting. They're not just another kind of noise, right? And also, they're not actually the sound of the earthquake, right? You might think, well, the earthquake is some complicated thing, and the wiggle is just whatever the complicated earthquake is. Actually, no, the earthquake is very, very simple. It's essentially a bang, right? And the wiggle is the result of that bang being propagated through the very, very complicated geological structures of the Earth and arriving at the particular station. So it depends on the path from the source event to the station that's detecting the signal. And so that's what the sound is that you're hearing. It's the sound of the path, not the sound of the event, so to speak. So what that means is that when another event occurs in the same place, it's going to look exactly the same. And here I've shown two earthquakes that were several months apart, but in more or less the same location. And you can see that there's a blue signal and a green signal here, and they are almost exactly copies of each other. And so these are called doublets, and in fact, when you look at the historical record of events, almost every event that we have a seismic recording of, you can find another event that looks exactly the same. And this is true no matter what the magnitude. Up to about 6, there's a perfectly linear scaling. So a magnitude 2 and a magnitude 4, they're 100 times different in size, but they're exactly the same shape. So that means that we can't have a simple stochastic model that says, oh, the wiggles are just random noise, right? Because that's not going to capture this repeatability. So in fact, we have to say that the wiggles are some function of spatial location of the source event. And so what we do is we have parametric models for both the template shape and size and the wiggle parameters themselves, which are represented by a mixture of a parametric and a non-parametric model. So basically, we use a Gaussian process to describe what the wiggle shape looks like as a function of space. And we have a wavelet model for the wiggles. There's 150 wavelet parameters. And with this approach, we get waveform matching, which means that when we see an event, we can actually find other events that look similar, and that tells us something about the location of the event. We can get something called double differencing, which is essentially it's kind of like super resolution. You get super accurate relative locations of events by essentially finding the locations which cause the two waveform signals to overlap perfectly. Just as an aside, it's interesting to note that the geophysicists are very happy to see Gaussian processes because we don't call them that, we call them Kriging, and they've been doing this since 1951. Whereas the rest of us have been doing Gaussian processes for less long. Okay, so just to show you that it works, right, we can take nearby events and they produce similar wavelet models. We can take distant events, they produce very different wavelet models. We can take the trained GP model, we can sample two locations that are close to each other that don't have any prior data. And indeed, those two locations, when sampled from the GP model, produce very similar looking signals, and distant points produce different signals. We can take a single station and ask what's the posterior location for some event based on the signal shape. And we can see that, yes, indeed, it does find likely places for the event to be based on the shape of the signal wiggles. And sometimes there can be more than one place, right? So that it doesn't mean that there's a single place. You can have a very similar looking wiggle from two quite separate places, but when you combine 5 stations together and ask what's the posterior distribution. So on the left, we see the model without wiggles, which is just based on essentially travel time and template shape. On the right, you see the posterior with wiggles. So you get about a 100-fold reduction in variance and a much more accurate location. Okay, so to summarize, this was a Bayesian approach to seismic monitoring. We did 2 systems. The NetVisa system works about 2 or 3 times better than the existing UN system. And the SIGVISA system, I think, could work much, much better than that, be much more sensitive and much more accurate. And I think in maybe 6 months to a year, we'll have some results that we can show on a global scale. Great. Thank you very much.
Thank you for a fascinating talk. We've got time maybe for one question.
Is there other information that could also be utilized by such a system? For instance, satellite-based measurements or interferometry, or I don't know. Because for you, it would probably be easy to combine different types of data.
So that's a very good question. There is hydroacoustic data, which we're not really expecting people to do tests in the ocean, but the hydroacoustic data would help a lot with tests that couple to the ocean. So actually, if you do it on land, it produces a wave in the ocean. The hydroacoustic system is incredibly sensitive, so you can drop a stick of dynamite on one side of the Earth and hear it on the other side of the Earth. It's really unbelievable. There is infrasound, which finds very, very low frequency vibrations in the atmosphere, and that can help. One theory is that when a test goes off, it lifts the Earth a little bit, and that produces a sound which you might find somewhere else. It's still very, very difficult because that's very subject to high altitude wind currents, and it's a much more problematic sensor. But it has been very useful for finding bolides, which are basically pieces of asteroid that hit the upper atmosphere and explode, often with the force of a nuclear explosion. So there was a 100 kiloton explosion over the Philippines a couple of years ago, which was detected by the UN system. There's also, it turns out, a disturbance in the electromagnetic field, which causes a slight blip in the GPS in the GPS coordinate system. And so that's one proposal for that. You might be able to detect nuclear explosions by looking very, very carefully at small errors in GPS. But the treaty doesn't allow that kind of stuff. So individual nation states can use whatever they want, but the UN can only use what the treaty allows, which is these stations and these forms of sensing. But yes, so after the effect, using radar to measure ground deformation is a very good way of finding a potential test site, because often the ground either puffs up or collapses down or does some combination.
So I'm afraid in the interest of coffee, we'll take the other questions offline.